Okay, so let's get started. So, I want to repeat a little bit of the stuff from last time, from last week. And we are still at class note 7. Class note 7 is a very long. There's a lot of stuff in there. And so from now on, it will be a little bit easier. Now we have to sort of connect a lot of information so far. And we're going to apply what we have learned so far, if we learn it. I don't know if we learned it. But we're going to apply what we have learned so far. We're going to, it's called connect the dots. Connect the dots, you have some dots, and then you draw a line between them. This is what we're going to do now. From now on, we're going to connect the dots. We're going to apply everything we have learned so far. And this is the, what should I say, this is like, the focus of this course is coming now. This is what we really wanted. So, sometimes, if you don't have a good teacher in statistics, then you will jump directly to what we're going to do now. But we did 12 lectures before we get to that point, because I want to explain how we get to where we are now. But I have seen courses in statistics, but they just jump directly to what we're going to do now. And we're going to do what's called inference. And inference is about collecting data, analyze data, draw conclusions based on what results you get when you do the analysis. So this is what we want to do. So, but I want to repeat a little bit what we did last week, because this is a difficult topic. I don't know, maybe I'm not so good at presenting stuff. I think the story I tried to tell you last week, there were some gaps in that story. Just a little bit, not a lot, just a little bit. But it does fill in these gaps. And let's have a look at what we talked about last week. So last week, we talked about the population. The population, this is the complete set of objects on the study. So, if I want to, before the election, maybe you want to do a survey to see what kind of parties will voters vote for. You want to see what fraction of voters will vote for the Labour Party, for instance, or the Progress Party, or the Communist Party, or whatever they're called. In that case, your population will be all voters within the country. So everybody who can vote at the election will be the population. In practice, we cannot ask everyone. We would like to ask everyone if we could, but we can't. So this is just a survey, and before the election, we just want to see what proportion of voters will vote for the Labour Party. So what we do is that we collect data. Maybe we ask 1,000 people, 1,000 voters, and we ask them what they will vote. And based on the answers we get, we will compute the proportion of voters that will vote for the Labour Party. We will get a number. Let's say it's 0.22, 22%. Let's say that it's 0.22. Is that the true proportion? Is that the true proportion of voters? 22%? No, it's not. Because the true proportion, that proportion is in the population, but the proportion you get in your sample is only based on 1,000 individuals, so you don't know if this is the true proportion. You don't know how close you are to the true value. Maybe the true value is 24%. And if you think it's 22, you make a mistake by 2 percentage points. You understand? So the point is that when you work with statistics, you want to say something about the population. You want to conclude something about the population. But you only have a sample. You collect a sample, 1,000 voters. And then you do your computation, then you see. And if you're lucky, you're close to the proportion in the true population. If you're lucky. If you're unlucky, you're very far away. Statistics is about to handle that difference between what you get in your sample and what you have in the population. How do we handle that difference? How do we handle that mistake? This is what statistical analysis is all about. If we didn't have this problem, we wouldn't be here today. There would be no statistics course. So if you could ask everyone, if you have access to the entire population, then there would be no point of being here. Then you will know the true answers to your problems. So all of the stuff we've been doing so far, all the probability theory, everything leads up to this point where we're going to apply this. We're going to work with limited information, we're going to work with a sample, and we're going to do computations, and we will make conclusions based on what we find in the sample, but we're making conclusions on behalf of the population. So this is what this is all about. Then we talked about how to sample. The way you sample is that you make a lottery. So you have your big population, and you need to select individuals from this population or objects. And the way you do this is by you do random sampling. Random sampling means that you select individuals randomly. There must be an equal chance of every individual in the population to be selected. Equal chance. The selection of one individual must not affect the probability of selecting another individual. So, and the way we do this is we use the lottery method. So we select randomly like a lottery. And so this is the way we do this in practice. So there are more fancy ways of selecting or collecting data, more fancy ways. We're not going to look at this here, but there are other ways to do things. And sometimes other ways are better than what we do here. But the point here is that we have independence. That is the requirement for all the analysis we will do. And if we do the lottery method, we are satisfying that requirement. Okay, in the population, there are some numbers. So if we look at all the voters in Norway, what is the proportion that will vote for the Labour Party, as an example? That is the true proportion. It's in the population. If we could ask everyone, then we could figure out the true proportion, the true fraction of voters who will vote for the Labour Party. If we could ask everyone. That number is called a parameter. It's a parameter. So when you sit on the subway, you're going to sit and say parameter, 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 and then you learn that this is a number in the population. It's a number in the population. If you're interested in some other phenomena, maybe you're interested in computing an average. If you have access to the whole population, you can compute the average. This is what we call the population mean. It's a parameter. It's a parameter. It's a true value that characterizes your population in some way. It describes some phenomena in the population. So how many parameters do we have? So we have the proportion, we have the mean value, but there are infinitely many other parameters that might be important to us. I have made a small table here, and here I have mu. This is the population mean, I have here the population variance. So if I have access to everyone in the population, I can also compute the variance. It's called the population variance. And notice the notation. This is the notation. This is called mu. This is called sigma to the power of 2. It's just a number. These are just numbers. We don't know these numbers in real world. We don't know these numbers, but they are there. So many people have this idea, if you don't know the number, then it does not exist. But this is not the way the world is. There are many numbers out there you don't know about, but they are numbers. They are fixed constants. So we have the standard deviation is this one here. This is just the square root of this one. It's a parameter. If we have two variables, x and y, you have the covariance, and it's sigma, then we use the subscript xy. This is the covariance. There's a true covariance. It's a number. We may not know it, but it's there. And we have the true correlation. So, and you know the true correlation. This is just the covariance divided by the standard deviation of x multiplied by the standard deviation of y. So that is the true correlation, and we use this letter here. It's the Greek letter rho. It's not a p, but it's a rho. And here we have the proportion. This is the true proportion of the proportion. Now, in order to find these numbers or approach these numbers, we cannot compute these numbers. They are known to us. But what we do is that we collect data, and then we say that we estimate these numbers. We estimate the numbers. And there are different frameworks for estimation, depending on the parameter. So what you see here, this is your estimator here. This is your estimator for the population mean. Notice here we use the uppercase X, because these are random variables. So it's what we call an estimator. It's a function of a random sample. So in this function, we put in all the random variables. Here, look at this. I use the uppercase letters. Also for the variance, I use the uppercase letters. This is an estimator of the variance. This here is an estimator of the standard deviation, estimator of covariance, correlation, and what you have down here, x divided by n, this is an estimator for the proportion. So x, this is a random variable, which is the number of, this is some frequency of some event. And then you divide by how many individuals you have, and you get the proportion. So we will look at some examples of this very soon. So, okay, if I apply my estimator on collected data, I get a number, and we call this an estimate. An estimate. So now you have three things to keep track on. Your population parameter, your estimator, and then your estimate. Your estimator is a random variable. Your estimate is a number. When you put all the data into your estimator, you compute some number, you get a number. This is your estimate. And so last time we looked at this example here. So I had here mu. This is the population mean. I have the estimator, and then I have the estimate. Fixed number in the population. My estimator is a random variable, and when I apply this random expression here to data I have collected, I get an estimate. Three things. So what we have here, number, random variable. Okay, if we want to study anything about statistics, we need to study the quality of estimators. And this is where we talked about the property of an estimator. And I introduced you to 3 different properties. Property 1, called consistency. What happens when you apply your estimator to a data set that is very large? And what happens when you make it larger and larger and larger and larger? Now, as n becomes larger, what happens? If you have a good estimator, then the estimator will produce estimates that converge to the true value. So in this case here, for instance, I'm applying this estimator here. This estimator here is consistent. That means that as n becomes larger and larger and larger, the number that comes out here approaches this value here. You understand? So when you apply this estimator, the number that comes out here, if you have a consistent estimator, the number that comes out here converges to this number there. We say that we have a consistent estimator. So when n becomes very, very large, we become very, very close to this number. Very important property. Then we looked at the second property, and that's called unbiasedness. And unbiasedness, that is about, it's not about n. Here we hold n fixed. We hold n fixed. And then we look at what happens on average. So for instance, if I apply this estimator here, what happens to this estimator here on average? If I apply this estimator and I compute an estimate here, what can we expect on average in the long run when we repeat the analysis over and over and over and over again? If you have an unbiased estimator, then your average will be this number there. The average of your estimates will be this number. Then it's unbiased, unbiased. You will be right on average. So it's like having a discussion with a friend. And then you say to your friend, it doesn't matter if I'm right now. I'm right on average. That what matters. Then you say that you're unbiased. So, and that is what we can hope for in statistics. We cannot hope to be right in one single go. If I collect data about the voters, I can be lucky that the proportion I compute is close to the true proportion. But in general, it will not be equal to the true proportion. But on average, if I repeat my survey over and over and over again, maybe on average I compute the true proportion because I'm using an unbiased estimate. This is unbiasedness. And then we looked at efficiency. And efficiency is relevant if we have 2 estimators for the same parameter. So you have different choices here. Should I use this estimator? Should I use this estimator? We have the median, for instance. This is an estimator of mu. And we have the sample mean. So, just 1 second, sir. So you have the median here. This is an estimator of mu, but also this one is an estimator of mu. So which one is best? This one or this one? Both these estimators, under certain conditions, are unbiased. That means on average, they give the true value. So this one will on average give this number. This one will on average give this number. Which one is best? Then we can use efficiency, the property of efficiency. We look at the variance. And then I had this example that showed that the variance of the sample mean is less than the variance of the sample median. That means the sample mean is more certain. In general, you are closer to the true value. There's less uncertainty associated with the sample mean. This is the reason why we like the sample mean. Under some conditions. Under other conditions, the world will be different. The world is a complicated place. So, onto something. Okay. When you compare the variance of one estimator to the variance of another estimator, when you do that, you need to have the same level of bias. And that's what I've been telling you last week. You need to have the same level of bias, otherwise you cannot compare. So in this case, with the sample median and the sample mean, there the bias is 0, because both of them will, on average, give the true value. So the bias is 0. So both of them have 0 bias, so they have the same bias. So then we can compare under some conditions. Under some conditions. So to do all these computations about consistency, unbiasedness, efficiency, complicated. So the way I make exercises for you, I make these like, let's say, easy to go exercises. It's a little bit like buying hamburger. It's quick to make and it's quick to consume. So, and this is the level we can expect in such a course here. So unless you are a very trained mathematician studying statistics, then it's very difficult to do the math behind all of this. But I can make some simple exercises where you work with variances and expectations because you know the tools for that, and then you can solve these exercises. And there's a handful of these exercises. This is sort of the level you should do. I would be happy if you follow what I'm saying now. If you can follow what I said today, I would be happy. This is good enough for me. Good enough. And you can solve this exercise. It's good enough. You're not going to be statisticians from this. From this course, it requires a lot more. Nothing wrong with that. You're going to do other stuff. So, but if you have an idea of things, okay? So what we do in class here is so that we get enlightened. You understand? That we know things a little bit. So when you go to the city, you meet a beautiful girl or a beautiful man, whatever. And then you know, I know 3 properties of estimators. And you have a deep and profound discussion about this. This is how you make friends. Maybe, I don't know. So I haven't succeeded with that yet, but okay. Otherwise, you can try the stamp collection also. Did you have some question there? No, this is just one example. So, one estimator is the mu. If I can find it again here. Here. This is one estimator. So I showed you this as an example because this is the easiest one to work with. But you have other estimators here. They will sort of have the same properties as this one here. So for instance, the sample variance have the same properties as the sample mean. So it's consistent, it's unbiased, and I also believe under some condition is the most efficient way to compute variance. So maybe the only way, I don't know. So if you well, try to notice here, we talked about this in the beginning of the course. Can you see? Everything you see here is based on summation. So this is what we call parametric statistics, and it works extremely well. Parametric statistics. Based on summation, and then you'll have all these good qualities. Like this. Okay, I think I tried to, I managed to sort of summarize a little bit what we did last week. Summarize it, and now you need to train on this so that you can solve problems with this. And there are some examples here. Actually, it's not so bad. Okay, so next topic. Interval estimation. And now it's going to be more practical, less theory. But there's a little bit more theory before we take the break, and then it will be more practical. So interval estimation. So if you're going to apply statistics in the real world, this here is what you want to see. So, okay. Here, this is the number line. This is the value 0. Here you have the positive numbers, here you have the negative numbers. As an example, suppose you collect some data and you compute some number here. You compute, let's say you have some data, you compute the average. And your average is located on the number line exactly there. So this here is our estimate. So we applied the sample mean, and then we get an estimate, here we get a number. I don't know, it could be 2.5. Should we say 2.5? 2.5. This is your estimate. This is what we call a point estimate. It's one single number along the number line. But you know that this estimate, it comes from a random process. You have used the sample mean, which is a random variable. So it's derived from a random process. That means that next time you collect data and you compute your estimate, maybe you're here. If you collect data again, maybe you're here. Maybe you collect data again, maybe you're here. You collect data again, maybe you're here. So you see, these estimates, they jump back and forth along the number line. So, wouldn't it be wise, instead of just looking at one number, let's say that we derive an interval. And then we say, this is an interval. This is, all the numbers in the interval are likely candidates for the true value. It's an interval, or an interval estimator. So, let's say that I specify this interval here. Let's say I have the value 1 here. And here I have the value 4. So now I have the interval 1, 4. And then I think that, okay, the true mean, this is the true mean in this case. Then I believe that the true mean is located somewhere in here. It's an interval. And so that can be very nice and very useful for us. So what I want to do now, I'm going to show you how does this work. And I'm going to show you how you can compute stuff with this. Notice that when we derive such an interval, usually it is a function of what we get here. The distance, so now there's a lot of things going on in this, yeah? But you see, the distance from here to here, this here, we call this the margin error. So this is the margin error, just right in here. And the distance from here to here, this is also the margin error. So this is sort of that distance here. That distance is the same. So if you go to the right or you go to the left. So you get your point estimate exactly in the middle. So this is the margin error. So now what you need to understand is that the number here, so if you compute the margin error and then you find the value 1 and then you find the value 4, these numbers, they are random variables. Since this one comes from a random process and you use this to compute this. Well, let me say it differently. You use the sample mean, this one, to compute this. And so the point is that you get a random number here and a random number here, so these are random. So an interval estimator, it gives you a random interval, it moves back and forth when you collect data, when you compute stuff. So, let me try to explain to you how this works. So in general, this is the form. So this is just what I sort of argued about here. So you have a point estimate. So PE, point estimate. And then you subtract some number here, ME. So your margin error. You add ME. So if you do both, you get a small number and a large number. And that would be, in this case, it's 1 and 4. There's a small number, there's a large number. and everything in between are sort of candidates for the true value that you don't know, because you don't know the population. And this is the way that we call it this a confidence interval. Confidence interval. So in this course, we compute intervals based on probabilities. So we're deriving probabilities. So before you compute your interval, you need to make a choice. There's something called the confidence level. And so there's something called 90% confidence level, 95% confidence level, or 99% confidence level. These are sort of common in real life. People use 90%, 95, or 99%. And when you apply these here, they will sort of dictate how wide the interval will be. So, and this is something you need to know. An interval that is very wide, so there's a big distance from here to here, is not very informative. A narrow interval is very informative. Imagine you have a friend, live abroad. Your friend is considered move to Norway, maybe have a job. Your friend asks you, what is the salary in Norway? And then you say, you specify an interval. You say a typical salary is between 550,000 and 750,000 a year, Norwegian kroner. That is quite informative, because now the individual that you talk to have a very clear idea of what is a normal salary in Norway. But if you give your friend the wider interval, if you say, a salary in Norway is between 0 kroner and 100 million kroner, that is not very informative. Oh, between 0 and 100 million, this is a very wide interval, it's not very informative. So to give a number between 550 and 750, that is much more informative. You want a narrow interval. That you can sort of control with the confidence level. So if you choose 90%, you get a more narrow interval. If you choose 99%, you get a wider interval. But the problem is that you have to give up something. So if you choose 90% confidence interval, then you will make more mistakes about the location of the true parameter. So you are allowed to make more mistakes when you make a conclusion. So you're giving up something to have something. So in real life, many people use 95%, sort of a benchmark. So it would be very useful here to introduce this quantity alpha. Alpha is 1 minus the confidence level. Alpha is important because we need it when we do the computation. So 1 minus the confidence level is your alpha. So 1 minus 0.9, if you choose a 90% confidence level, and you want to find alpha, then it's 0.10. 1 minus 0.9, 0.10. So that is your alpha. So the alpha is more a technical number that you need to do the computation. Okay, it says here, when computing a confidence interval, one is applying a procedure for which the true parameter is contained in the interval with this probability here. This is your confidence level. So this is a technical way to write the confidence level. So if you want to compute a 95% confidence interval, then you are applying a procedure for which the true parameter is contained in the interval with 95% probability. Notice here, you don't know what this means, but this has some implications. It says one is applying a procedure that in 95% of the cases will contain the true parameter. So that is how this works. Okay, what does it say here? Important. It says something with importance. It says, it would be wrong to claim 95% chance that the true parameter falls within the bounds of an already computed confidence interval. So you see here there is some conflict in this statement here, and there is some conflict in this statement here. I will show you in just a second how this works. Okay, let us try to see if we understand confidence intervals. Remember what I said here? These are random values, random value. These confidence intervals, they jump back and forth on the number line if you collect data many times. And I have exactly done this. I have this example 2 here. So let us have a look. Let me see. There. Okay. So we're going to do a simulation experiment. Exactly what we did. Remember, I showed you this on R. We roll the die. This is the same, almost. It says, in performing the experiment, we generate 50 different random samples. Okay? So, I'm generating 50 random samples from some population. Okay, every sample, I have 10 observations, I have 10 data points. So here I hold n fixed at 10. So n is equal to 10. The population mean is 50, because this is an experiment, so I can control the population mean. And this is 50 in this case. The variance is 100. This is something I choose when I set up the simulation. Based on the 50 data sequences, we computed 50 different 95% confidence intervals. I'm using a procedure to compute a confidence interval, 95% confidence interval in this case. The 50 intervals are plotted in the diagram below. The horizontal line in the diagram represents mu. And the numbers along the x-axis represent the 50 samples. Okay, try to look here. Can you see here? My mu is 50. I have it here. This is my mu. Can you see this straight line? This is the 50, the mu, the true value. Okay. In the first sample, I find this interval here. So you see here now the interval here. The lower value of the interval is a little less than 40. You see this? The upper value is a little bit more than 50. In this case, my confidence interval covers mu equals to 50. The 50 is in the interval. If I claim that my interval covers the true value, then I am right. If I conclude that, I'm right. Let us look at the next confidence interval I computed. The lower value is around 40. The upper value is around 55. Again, the true value is in the interval. My procedure to find the true value, the interval I have computed, it contains the true value. This is what we want. That's the whole idea. And then we continue like this. We can see here the fourth interval also contains the true value, and the third one. Pretty good. But then you see when we get to number 5, here we miss. The lowest value is above 50. The interval does not capture the true value. So here, if I claim that the true value is in this interval, I'm making a mistake if I make that claim. And we can continue like this, and we see there is only one more here. Again, this interval here does not cover the true value, but in most cases it covers the true value. And what you find is a confidence interval is, if it's 95% confidence interval, as in this case, that means that you are wrong. There would be 5 cases out of 100 where the confidence interval will not cover the true value. This is a confidence interval. So if you choose 95%, that means that for every 100 analysis you do, you will be wrong in 5% of the cases if you claim that the true value is in the interval. So now you can imagine that If you do a 99% confidence interval, then it's only 1 out of 100 where you make a mistake. But the problem with that is that then your intervals have to be much wider to be sure to get to the 99%. You get wider intervals, less informative. So you have to make a trade-off between how often you're wrong and how wide the intervals are. 95% was okay. If you take here, in this case, 2 divided by 50, then you get roughly the amount of mistake you make when you claim that the true values in the intervals. And I computed it here, then I get 96%. So why is it not 95? It's because I only tried 50 times. So if you continue with this, you will see that this number here will be 95. So that is the reason. Okay? Do you know what a confidence interval is now? Do you have an idea? It's not that difficult. But you need to think about this a little bit and you know, it's like something that needs to mature. Okay, we will start with something very easy. And I'm not going to show you how you derive the procedure for how to compute the confidence interval. I'm just giving you the formulas. And then I say to you, apply these formulas and do the computation. That's it. I'm not showing you how to derive this. It's not very difficult. If you're very interested in this, I can show you. It's a little bit of computation. I'm just giving you the formulas. Okay, notice this here. Confidence interval for the population mean, and here, with a known standard deviation. Known standard deviation. And how do we do this? We use this. This is our point estimate, plus minus the margin error. And the margin error is computed with this formula. Notice this one here called Z star. This is a constant that you find by solving this equation. I will show you how to find these numbers. Very, very easy. And when you have found Z star, you go ahead and you apply this computation here. You get two numbers, a lower number and a larger number, upper number. That is your interval. And Z star is found in this table here. So if you're computing a 95% confidence interval, then Z star is 1.96. You can look it up in this normal table. If you're using or computing a 99% confidence interval, then Z star is 2.576, and so forth. This table here you just applied, but you can find the numbers in the usual table for the normal distribution. And there are some requirements for this to work, always, assumptions. I think we take the break, and then I'll show you how this works with some numbers, and we come back here no later than 3 o'clock, no later. You can come before, that's okay.